Hello and welcome to our final worksheet walkthrough video of the summer semester. This is worksheet 12, where we're going to be talking about sorts. Okay, so this is a broad overview of sorts. Sorts are, of course, a huge part of computer science. They're a really good step into kind of understanding algorithms because they are all algorithmic and have some nice theoretical implications. But right here with question 1, we're going to start just with the basics of making sure you know how to do every individual sort and how it actually works. So let's just get into it and do each sort. So first thing we're going to do is we are going to sort with insertion sort, selection sort, some other sorts. Now, here is the list of data we're sorting. I've redrawn it a few times. One thing to note here is we have a 4a and a 4b. This is because it's going to be relevant when we're talking about stability in sorting, but these values, basically, they both have the value 4. The a and b are just to differentiate them. You can also think of them as like 4 and 4 prime, right? They're both 4. They just have different, it's just so we can keep track of which one's which, because remember, stability is about seeing if elements that are the same value switch precedence. Anyway, so insertion sort. Let's start with the basic one. So insertion sort, all we're going to do is we're going to go left to right, and we're going to see at every successive index if we need to swap with the previous element. So I'm going to start by drawing a big line here. Basically, everything to the left of this line is unsorted, or is sorted, sorry. Everything to the left is sorted. Everything to the right has not yet been sorted. So when we start, we haven't sorted anything, so I'm going to put the line to the left of the 2. And then we're just going to go line by line and do some swaps. So first thing we're going to do is we're going to look at the 2. 2 is the first element in our insertion sort, so trivially, it's already sorted, right? Because we're saying, is there anything previous to this 2? Is the element before the 2, is that less than 2? And of course it's not, because there's no element. So let's move that up. Okay, so now we're going to look at the 1. So what we do is we say, okay, should we swap 1 and 2? And the answer in this case is yes, because 1 is less than 2. So we'll make that swap. 1, 2. And then we would also say, well, do we need to swap 1 with the next thing previous? But there is no next thing previous, so you can just stop right there. Great. So now we've sorted up to this point. So we look at 8. Does 8 need to swap with 2? The answer is no, because 8 is bigger than 2. So all sorted, we can keep going. Notice that we don't need to check if 8 needs to swap with 1, because we know if it swaps with 2, we know that if it doesn't swap with 2, it's not going to swap with anything that's prior to 2, because everything prior to 2 is less than 2. Okay, great. So now we have 4a. So 4a, remember, it just has the value 4. We say, should we swap these two? Should we swap 8 and 4? The answer is yes. So let's swap them. 4a, 8, great. Now we sort it up to here. 6, again, we just say, do we swap 6 and 8? We are going to. Great. 7, we say, are we going to swap 6 and 7? We're going to, because 7 is less than 6, or 7 is less than 8. We're up to here. Now we say 9. Are we going to swap 9 and 8? We are. Great. So now we're up to the last element. The last element is going to be a little interesting, though. So this is 4b. So first thing we do is just same as normal. We say, okay, do we want to swap 9 and 4b? And we do, because 4 is less than 9. So we do this swap. But now we need to keep applying to prior elements. So now we want to say, is 4b less than 8? Do we want to swap here? And the answer is yes, we do. Then we say, okay, is it less than 7? It is. So we just keep going, basically, until we get to a point where we don't need to swap anymore. Is 4 less than 6? It is. And then we say, is 4 less than 4? And it's not, right? It strictly isn't. So now we've sorted everything. This line can go all the way over here because we're done. And notice everything is sorted. So that's what we do. We just look at the element that is previous to the one we're looking at. We say, should we swap these things? If so, we do. If not, we just move on to the next thing. Question about stability here. The question is this sort stable? And you can see that it is stable, right? Because we define stability as equal elements not changing their relative position. What does that mean? So basically, notice that in this original list, 4b started after 4a. So if the sort is stable, that means that 4b will never end up in front of 4a, right? And notice here, that is the case. That is true, because we only swap if an element is less than that element. So there's no way that 4b is ever going to jump over 4a, basically, is a way you can think of it. Great, so insertion sort is stable. That's the process for actually doing it. Okay, selection sort. So let's move on to selection sort. Basically with selection sort, what we're going to do is rather than doing a bunch of swaps, we're only going to do one swap per element. And we're basically going to run through the array, find the minimum element, and then swap that with the 0th position. And we're going to keep repeating that process. So again, we can have this kind of line of saying, okay, everything's sorted. And then what we're going to do is we're going to look at the element to the immediate right of this line, right? The next element we want to look at, and we're going to swap that with the minimum element of the array. So basically all we do is we run through the entire array and we find the minimum element, which is just going to be 1, right? And this is just going to be a simple comparison. Just look for the minimum, right? So we're going to do this. And then we're going to swap this with the element that is immediately right of the line. In other words, the 0th element, right? So we're going to swap 2 and 1. Great, and now our line can move over here, right? So now notice everything to the left of the line is sorted, everything to the right is not sorted, right? And we just keep repeating this process on smaller and smaller sections of the array. Now we look for the smallest element in the entire array that is to the right of the line. In other words, that is excluding the part we've already sorted. We're just going to find it, it's 2, and then we swap it with the element that's immediately right of the line, which is itself, so we're not actually going to do a swap. We're just going to keep moving on because that part's already sorted. Great, and then just keep going. What's the minimum element remaining in the array? We're going to scan through. It's either 4a or 4b. We don't actually know. Either one could come up first. Let's say in this situation that it's 4b. Then we're going to swap 4b with 8. Like this, move our line up. Look at the rest of the array, find the minimum element, it's 4a. We swap it with itself with 4a, so no swap. Look for the minimum element, it's 6. We're going to swap it with itself, so nothing happens. Look for the minimum element, it's 7. Swap it with itself, nothing's going to end up happening. So we're just done with that part. We're all sorted up to here. Now we look for the minimum element, it's 8. We swap it with 9. Like that. Finally, trivially, we look for the minimum element. There's only one element, so of course it's 9, so we don't need to swap it, and it will just be there. Okay, and that is how we sort something with insertion sort, basically. Okay, notice on stability, we ended up with this 4b before 4a. That is because selection sort is not inherently stable. It could be stable in some runs, but it's not guaranteed, so it's not a stable sort generically. Okay, next one, merge sort. So basically, what we're going to do with merge sort is we're going to break our data into smaller and smaller subarrays, and then we are going to sort it in its subarrays. So basically, the first few steps of merge sort, we're not actually going to change anything. We're just going to sort things into subarrays. So right now, we have 8 elements. Then what we're going to do is we're going to split this into 2 groups of 4 elements, and then we're just going to keep splitting. So we're going to split it into 2 groups of 4 elements, then we're going to split it into 4 groups of 2 elements. In other words, we're going to split each of these subgroups recursively into a further subgroup. And then these groups of 2 are still too big for us, so we're going to split them all into groups of 1, like this. I tried to make the line sizes kind of correspond to the different runs. Let me actually do it. Let's color code it to make it a little easier. This is going to be our first split. This is going to be our second split. And this is going to be our third split, right? And at this point, everything is down to a size of 1. Okay, so the question with merge sort is basically then, how do you sort an array that is only size 1? Well, trivially, it's already sorted, right? So our first part of merge sort is breaking it down into these size 1 arrays. Once we've broken into size 1 arrays, those are all sorted. So now we can combine sorted arrays. So after we do that, we're going to be at this step again. We're coming out of the recursive call, right? So now we have arrays of size 2. So we say, okay, let's sort these smaller size 2 arrays. So this is going to be really easy for us. Whoops. This is going to be really easy for us. How do you sort 2 and 1? Well, it just ends up being 1 and 2. How do you sort 4a and 8? It's just going to end up being 4a and 8. How do you sort 6 and 7? It's going to be 6 and 7, then 4b and 9, right? Notice that we have sorted that we sorted all of these by 2s. Okay, then we come out of the 2-step and we're going to sort them all by 4s. So now we combine these arrays into size 4 arrays. So how would you sort this? Well, in this case, it's actually already sorted, but it would be 1, 2, 4A, 8. And in the next one, it would be 4B, 6, 7, and then 9. Great. And now we're finally going to come back out to the final step where we have all 8 elements. So we're going to combine our 2 length 4 arrays into one final sorted array. And at this point, we're basically just going to sort it into its final order. So we're going to end up with 1 and 2, 4A, 4B, 6, 7, 8, 9, right? So we broke everything down into size 1 arrays. Size 1 arrays are trivially already sorted. Then we sorted those size 1 arrays into size 2 arrays, the size 2 arrays into size 4 arrays, size 4 arrays into size 8 arrays. And we could keep going if we wanted to. Okay, so stability here, this actually is a stable sort. I'm not going to go too much into it right now, but basically, if you do it yourself, you can see it. But it's basically because of the way that we are sorting these sub-elements, we can sort these sub-elements stably, and then we end up with everything being stable. If we are stable at every step along the way, we're going to end up stable at the end, basically. Okay, that is that. And now we do heap sort. Okay, so heap sort, we take our data. First thing we are going to do is we're going to turn it into a heap, and then we are going to call our heap every time to sort things. So I'm going to assume that you know how to turn things into a heap already, so I'm going to kind of skip that step and turn this into a max heap. So the max heap that would be created from this is going to look like this. This is the max heap created from the data. And just so it's a little bit easier to understand kind of in our heads, I'm going to also write the tree representation of it. That's going to be a lot easier to keep track of. Okay, here's the tree representation of this heap. So now this is a max heap, right? As opposed to the min heaps we've mostly been working with in this class. And all we're going to do is we're going to just pop off the maximum element every time, and we're going to sort our array back to front. We're going to get the biggest element, go all the way down to the minimum element. So the first thing we do is we pop off the the max, which is going to give us 9. So we're going to pop this off, and then we're going to do our normal heap operations. We take the bottom rightmost, put it at the top, and we're going to swap it down with its maximum element, not its minimum element, because right is the max heap, not a min heap. So this is going to be 4b here. This is going to be 8. Do we need to swap 4b again? And we do. We need to swap with 7. Like that. Then we pop off the maximum again. It's 8. Take the bottom rightmost, put it up here. Now we're going to swap with the maximum. So we're going to swap with 7. 7 and 2. And then we're going to swap here 4b and 2. Then pop off the maximum, 7. Replace it again with 2. Swap with the maximum of these two. It's going to be 2 and 6. And then swap with the maximum of these two, 4a and 2. Great, pop off the maximum, 6. Put 1 on top. Then we're going to swap down. It says if they are equal, you should sync with the left. So we're going to swap this 4a up. And then 1 here, and we need to swap 2 and 1. Pop off the max, it's going to be 4a. Put 1 on top again. Notice that 1 and 2 got a lot of time on top. Swap with the max. So you have 4b, 1, pop the max off, 4b. Put 1 on top once again. Swap 1 with 2. Then pop off the max is 2. Hopefully you can see if we pop off the max again, it's going to be 1. So that's how we're going to do the whole process, right? I did this mostly based off the tree representation because that's a little easier to understand. But this is how it would end up if you did it with heap sort. Notice here, heap sort is of course not stable. Here's an example of why it is not, right? And that's just because the relative orderings of the elements are not going to be preserved during the heapification step. So it's not necessarily the case that we're going to end up with a stable sort. Okay, that one is probably the most kind of grindy to do just because you have to turn it into a heap and then do all these operations, but hopefully it's not terribly complicated. If you're familiar with heap operations, you're just doing a bunch of those out on paper. Great. I think there's a typo in the worksheet because I'm looking at the solutions of it and it has quicksort listed, but there's no quicksort on this version of the worksheet. So I'm just going to do the quicksort version anyways, and then I will add the quicksort prompt to the worksheet later because it looks like that is just a typo. Okay, so let's do quicksort. Okay, so we're going to start with 2, 1, 8, 4A, 6, 7, 9, 4B. This is quicksort, and this is the standard quicksort. So this is going to be left pivot. This is not for partitioning. You may have heard that. We've taught that in past versions of the class. It's not in scope for the final. We're going to do just the standard run-of-the-mill quicksort. This is normally what people are talking about when they say quicksort. Okay. Yeah, so basically, quicksort is a little bit more complicated, but it's going to be the fastest sort in practice. That's why it's called quicksort. Here's basically how you do it. First thing is you're going to select a pivot. There are a lot of ways to select a pivot, but the way we're probably going to do it is we're just going to take the leftmost element and choose it as our pivot. So what we're going to do is now we're going to choose 2 as our pivot, and we're going to go left to right, and basically we're going to go left to right on our array, and basically everything that is less than 2 we're going to put on the left, and everything that is greater than 2 we're going to put on the right. So if we start with 2 here, that is our pivot. Remember, let's just look through the array left to right. So 1 goes to the left, 8 goes to the right, 4A goes to the right, 6 goes to the right, 7 goes to the right, 9 goes to the right, 4B goes to the right. Notice we really split this into one pretty big section and one not so big section, but we're just choosing the leftmost pivot and it just happened to work out that way. Okay, so then what we're going to do recursively is we know that 2 is sorted at this point, right? Because if everything to the left of 2 is smaller than 2, everything to the right of 2 is greater than 2, then 2 must be in the right position, right? 2 is definitely sorted. This part is not sorted yet, this part is not sorted yet, but all the right elements are there, so 2 is sorted. So now what we're going to do is recursively sort this half and sort this half. So with this half, it's pretty trivial, right? Because we're going to say we only have an element 1 array, so the pivot is 1. There's nothing to put on the left side, there's nothing to put on the right side, so everything's already sorted. So because this is size 1, I'm just going to bring this down here and say we're already done. This one's a little more interesting though. So we're going to do the same thing as we did before. We are going to take the element that is at the leftmost, make that into our pivot, which is going to be 8. So we're going to pivot around 8, and then we just go left to right on the remaining elements in this section of the array, and we put the smaller ones on the left, the bigger ones on the right. So 4A is smaller, 6 is smaller, 7 is smaller, 9 is not smaller, 4B is smaller. So you end up with that. Great. So keep in mind, everything that is underlined has been a pivot and is therefore sorted. So the next 2 arrays we need to recursively sort are these ones. Again, 9 is trivially sorted because it's an element 1 array. So I'm just going to kind of write it down here. The interesting one is this block of 4. So we're going to take 4A, we're going to make it our new pivot. And we're going to say, if you are greater than or equal to 4A, you're going to go to the right. If you're less than, you're going to go to the left. So going left to right, 6 is bigger, 7 is bigger, 4B is the same size as 4A, but we're going to put it to the right just because we're deciding to break ties by putting everything to the right. Okay, so we didn't really sort anything aside from 4A here because, again, we didn't split it up very well, but that's fine. Now we're going to sort these 3 elements. We're going to choose 6 as our pivot. So what's going to end up happening is everything is going to go that is bigger than 6 is going to go to the right. Everything that's less is going to go to the left. So 7 is bigger, 4B smaller, right? So we go like that. Keep in mind all these other elements over here are already sorted. So I'm just going to copy them down. And now we need to sort this half and this half of the array, the things that have not been pivots. But again, trivially, it's already sorted because they're length 1 arrays. So we're going to end up with this. We have our fully sorted quicksort array, right? That's how it works. Quicksort is not stable generally, but it can be stable if we kind of create this specified tie-breaking routine, right? Remember how we said everything that is bigger stays on the right. If you create a tie-breaking routine, basically, that says if you're equal value and you're already on the right, stay on the right. If you're equal value and you're already on the left, stay on the left, then you can make it stable. So generally, we wouldn't necessarily consider it stable, but if we define our tie-breaking algorithm correctly, we can make it stable. Okay. Anyways, I hope you enjoyed that. That is how you do these sorts mechanically, and we'll talk conceptually about these sorts a little bit in the next video.